Hey everybody, here's block day 2 asynchronous work. There's method in my madness. You've used 3 different methods for solving systems of equations: graphing, substitution, and linear combination. Describe how to use each method and the characteristics of the system that makes this method most appropriate. Okay, so graphing. Alright, so let's type some things out. Well, you're going to have 2 equations. 2 equations where you will input at least 3 points to determine the line on the graph for each equation. Okay, so why is that important? Well, let's make it a little bit smaller. Okay, well, why is that important? Because 2 points make a line, but you might make a mistake and it might be off. So if you have 3 points and you connect the dots and one of them's off, then there was an error, and that helps you correct your error, having 3. Although 2 points make a line, 3 checks your error. So what else? You're going to have to set up proper scales and label your X and Y axis. And then, this is only good. This method is only good if the numbers line up. What do I mean by that? Like I've said in class, graphing is more of an estimate for showing your understanding after the fact. I mean, this method is most appropriate. Let's move Mr. Schultz away here. This is most appropriate when the equations are both written in, y equals mx plus b form, also known as general form or slope-intercept form, and the values are reasonable to graph. So if they hit at 25.5 and you try to graph that, you can't really estimate that on your graph if you're drawing it by hand. I think I spelled nope, not recommended to graph by hand. You shouldn't be using a graph by hand. You should, if you are, you should have a ruler, okay? All right, the substitution method. Well, let me show you which, you should use, when this is in y equals mx plus b form, when one of them is like that, and then you had like 2x plus 3y is equal to 10, then you can plug in this right here. When one of the forms is in slope-intercept form or general form, you can plug it in. You don't have to isolate for the variable to plug it into the other one. So, but if we didn't have that, we would still, let's choose purple so that you understand that it's a different one. If it wasn't isolated already, you would choose one equation to isolate or solve for one of the variables. So that's the first equation. Then substitute the value for that variable into the second equation. So we have our first variable right here. Here's first variable, our first equation. Now here's our second one. Next up, that would make our variables go from 2 to 1. In this case, we'd be getting rid of our y. And so then we would solve this new equation, solving for a remaining variable. After that, once we get the value for the variable, once we get the variable's value, substitute that into the other equation, the first equation. Solve for the other variable. So in this case, we'd solve for x, then take that value for x and plug it into the original equation, solve for x. All right, so let's say, so like I was saying, this method is best when one of the equations has already been, you've already had the work done for you. Like, look, this y equals mx plus b, like the y is already by itself. So this method is best when one of the equations is in slope intercept form, or y equals mx plus b, or when like x is by itself or when y is by itself. That doesn't matter. All right, linear combinations method. Now, this is my new favorite one. I used to not like it as much. Like, and when I really first taught this in like 8th grade, I didn't like it as much. And now I'm like, ooh, I like it now. Now, standard form. Let's write down what a standard form. Standard form looks like this: ax plus by equals c. And so that's like when both of the equations. Well, let's put like 10. When both of the equations let's put 4. So let's talk about this in terms of this guy, okay? Let's go back to black. All right, so to determine if any of the, coefficients, any of the variables in either equation are additive inverses. So basically, look at this: 4x plus what equals 0? Negative 4x. Okay, no, that doesn't match up. 2y, negative 2y plus 2y equals 0. Does that? No. So x and y don't have any additive inverses. However, if there is not an additive inverse, make it through multiplication. So sometimes you'd have to, sometimes you would multiply both equations by different numbers. So if you had like 2 and 5, you'd multiply the top one by 5 and the bottom one by negative 2, and you get 10 and negative 2, or I'm sorry, 10 and negative 10, and add those together, gone. But in this case, we would just have to multiply the bottom one by what number? 2x times what will equal negative 2x? Okay. So then make sure to line up the correct variables and add the two linear equations. One of the variables should have been eliminated through, eliminated through a linear combination. So we should, like on that, the 4x minus 4x would go away, and then we'd be left with y's. So after that, you'll have one variable left. Solve for the remaining variable, and then input its value into one of the equations and solve for the other. So after you solve for one, you have to solve for the other. That's it. And now I would want to check both equations to make sure I got it right, to make sure that they're, check my result, see if it's correct. So when is this good to use this? Linear combination is perfect to use when both equations are in standard form. Thanks everybody. This was block day 2 asynchronous work. We might have watched this a little bit earlier, but I hope you guys have a wonderful day. Bye everybody.